All right, so what's good, what's bad?
Did you incorporate a third color?
Third color? Why would you need a third color? You don't want to screw with perfection.
Yeah, like everything has like three, like you have primary, secondary.
Is that really a thing?
Yeah, like team jerseys, there's always three colors.
Well, okay, well, but historically, so we got to go, I mean, so awesomefat.com, which I actually, the site's just, I'm revamping the site now, but I mean, it's been around since before 2000. So historically, the color, it's been white and red, or we've had black logos, so like on stuff, but this has kind of been the color contrast for a while. So I'm not sure we need a third color.
I have an idea.
Yeah, what's the idea?
You should wrap the whole car pink and then put the Awesome Fat logo on top of it.
Well, why did I just buy a pink Tesla to begin with?
I don't know, because you didn't.
Actually, I don't think they make pink Teslas, so I might need to wrap the whole car pink. I do like pink as a color, but Awesome Fat has always been, it's like the color has been awesome, always Awesome Fat red. So like, does it, my wife says I'm ruining the car. That can't be true, is it? You think it's missing something? It's like a Mr. Gonzalez logo. Yeah, so that's getting installed Monday. Is the plan. So sometime before Monday, that's hopefully the site is updated. Okay. All right, so I think last time we got the previous lab working, right? Where we had the parents collecting children until, well, collecting process IDs for their children until the parent received the interrupt signal. And then the parent went through and killed off all the children using the kill function, which targets a child process, which sends a signal to a very specific process ID. So we had a loop that went through and sent the specific signal to that process ID multiple times. All right, so now to revisit the lab before that, where we had it's similar as a starting point, right? Where the parent is spawning child processes. The parent starts off with some number of hit points, right? Parent, you know, maybe has 15 hit points, something like that. And then, yeah, it just for no good reason. It just, this is what it'll take to kill the parent, you know, if somebody was interested in killing off the parent. And then the parents start spawning off child processes, and the child processes are then in communication with each other, right? So if we were to draw a picture of this, we have our original parent. So we'll color code that like that. And then we have child processes. We'll just give ourselves like 3 of them here. All right, and we'll go ahead and assume that this parent has an HP of 3, something like that. All right, so the parent's going to go through and keep spawning off child process, child process, child process. Unbeknownst to the parent, the kids are ganging up on the parent. All right, so now the question is how do the kids know how many hit points the parent has? Let's start with just that question. How can we make the number of hit points available? How do we make the number of hit points the parent has something that the children now know?
Make it a global variable.
Okay. Do I have to make it a global variable?
Technically, no, because when you fork a process, it inherits everything that the parent process had.
Yep, so the parent gets a copy of all memory, right? So even if it was a local variable inside of main called HP, all the child processes would get access to that variable. Now, maybe to your point, Noah, they wouldn't have access to that variable inside of the signal handlers. So if we wanted them to have access to that variable in the signal handlers, we would need to make it global. So it's not that the child processes didn't have access to the variable data, just the scope of that variable would be the same as it was in the original process. All right, but the punchline here is that we don't have to do anything special other than make sure it has the appropriate scope for this variable HP, which is a plain Jane integer, for this guy to be available to all the child processes. All right, we don't need to do anything crazy with shared memory or anything like that. Okay, so as these child processes are being born, they're able to ask the question, how many parents, or what's my parents' hit points? No problem, right? All right, but now we've decided that the children here, they're forming a group to assassinate mom. All right, this is all Mr. Gonzalez's plan. It was a thing. Did I tell you about the coyotes in our neighborhood now? Now there's a cougar. There's a cougar sighting in our neighborhood. And Mr. Gonzalez wants a new kitty cat. So now I'm in charge of going out and getting the mail from like dusk on. Why is she sending me out with cougars? I don't get it. How did I get onto cougars? Oh, Mr. Gonzalez, the plan, the evil plan. All right, so these children are following Mr. Gonzalez's evil plan to kill off mom. And so one thing, I mean, so all these children know about the parents' hit points, but they don't necessarily know about each other, right? Because they're going to decide, I think in the lab we said that each child is able to do 1 damage, right? Child just little kidney punch, right? So each child already knows how much damage they can do. So we just have to have enough children to equal the number of hit points. But when this child is born, they know that mom has 3 hit points. When this child is born, they know mom has 3 hit points, but they don't know about how many other children there are. So the question is how do we make these children aware of the number of total children? So somewhere, go ahead.
Can you store the process IDs in like an array or something? So that's how you would communicate with each other?
Okay, so the question is from the parent's perspective. Parent can keep track of the number of children spawned. So really we got 2 different pieces of information we need to keep track of here, right? The parent can know how many children there are, but then specifically if these children are going to communicate with each other and say, hey, it's time to kill mom. We're getting a lot of sound bites here for the soundboard. Okay, they're saying, hey, it's time to kill mom. They need to be able to target each other and say, okay, it's go time, attack. All right, so what does each child need to know about? Well, they need to know about mom's process ID. Can each of these children get access to their parents' process ID? Do we have to store that somewhere, or can a child process ask for their parents' process ID? We have 2 functions, right? Get PID and get PPID. Get the parents' process ID. So it doesn't matter whether these children know about each other, they all know who mom is. So every single one of them can send a signal directly to the parent. That communication channel is available. We just have to pick what that the kill signal is, right? That's going to go back to the parent. Maybe it's sig kill, but you know, whatever. But these children do not know about each other. The parent, specifically, they don't know. The children don't necessarily have to know about each other in order to accomplish this task. We probably want them to know about each other since we're working on inter-process communication. But at the very least, the children need to know about the number of children that have already been spawned, right? The parent can keep track of that information, can they not? Parent can keep track of that information. But how do they make that information available to the child? So let's say that the parent, I don't want to discount what you said about the collection of the array. I think we're going in that direction, but let me go here. So we say num children. Initially, we had 0 children. Then we had 1, then we had 2, then we had 3, right? So one thing that we might be interested in looking at is how can the children know which child number they are? Was I the firstborn? Was I the secondborn? Was I the thirdborn? Okay, so we want to look at how memory is copied. So we're going to go back over here. We're going to do kind of like a halvesy approach to this. Can I close like most of this? Close all of it? Close others, close others. Nailed it. And then we're in signals. And we're in lab and we're in one shot, right? And we gutted most of it. Okay. So here inside of one shot, we're already calculating our parents' hit points. Now we're also going to say int, here, we're going to make it global, just like Noah suggested. That way we have access to it from a scope perspective inside of our handlers. All right, so the only reason we're putting it up here, num children, will start off at 0, is because we want to have access to that variable inside here, as well as inside main. 100% scoping thing, not a inter-process communication thing. All right, so each time through, when we create a new child, we're going to actually go ahead and we're going to say the purpose of this loop is to create children. That way, because we can decide, does the first child, do they think that they're child number 1, or if their child ID is 0, they're the first child? Doesn't really matter as long as we follow that, but we'll go ahead and we're going to say num children plus plus first. Okay. Hopefully I'll stumble upon it here in a few minutes, but there is an interesting thing to consider with the plus plus operator dealing with shared memory. Shared memory is not defined. Well, the plus plus operator is not defined for shared memory. So you can say shared memory, some integer space in shared memory equals that plus 1. That works, but that plus plus does not. So kind of interesting things when you get behaviors like that. So sometimes our shortcuts, we have to consider those shortcuts came after some of the primitive shared memory stuff that's been around for a while. And a lot of times those shortcuts weren't necessarily considered for support with things like shared memory. You know, this isn't like a major deal, but it's kind of one of those little idiosyncrasies that you maybe wouldn't consider, and like, well, why isn't this variable going up? And I'll try to show it once we convert over to shared memory for this. Maybe try to remind me, and I'll try to prove that that guy doesn't make that change, because it is an interesting caveat when you're sitting there like, well, why isn't this incrementing? I'm clearly incrementing it, but it's a thing. All right, so we'll go ahead and just increment num children here. And this isn't shared memory at this point. This is just plain Jane integer. Plus plus is defined for a plain Jane integer. We're good with this. All right, then we'll go ahead and create the child process. And what happens here? So the child process registers themselves with sig user2, whatever, blah, 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 and then waits for a signal. The parent sleeps for a second, then is going to send a signal to the parent, or to the child, sorry. We'll send sig user2. So the child has registered with sig user2. The parent waits a second, then kills, well, then sends to that child, because the parent has the child's process ID, right? Sends it the SIG user 2 signal. And we're just going to go ahead and show what does the child know in terms of numb children. All right. So here's our number of hit points for our parent. And then let's also do a I am child number. Something like this, and this will be numb children. Okay, and then the child dies. So child just says, hey, I know about mom's hit points, and I also know which kid I am, or was. Well, am temporarily. Okie dokie. So all the parent does is waits a second, then calls the kid so the kid can show us what does it know. This is C, right? All right, so the first kid knew they were kid 1, the second kid knew they were kid 2, third kid knew they were kid 3, and then this is a nonstop situation here, right? So go ahead and kill off the parent there. All right, so the kids are getting a copy from the point in which the fork system call was called of the current state of memory for the parent, right? So the kids have access to that stuff. Now, let's keep going down this path. It was mentioned that, hey, maybe we keep track of an array of the process IDs for the children, right? At the very least, the parent maybe wants to kind of have a collection of, they should know what their kids' names are, right? Their names being the process ID. It's a randomly, why don't we do that? Why don't we have randomly generated names for kids? They do it in video games where you can just keep hitting random until they get you a new name. Why don't they just use the same video game thing like World of Warcraft uses for generating your character name? Wait, hold on. I can't tell. Is that a good or a bad way? It's a bad way. Okay. Oh. All right. Oh. Man, I thought that was a good idea too. Saves all sorts of trouble. Because I think parents fight over the name sometimes. Or sometimes now you have all these really, I'll be nice and say creative names, but some of these names are out there. You got symbols and stuff in them. Wasn't there that thing a couple of years ago at the airport where there was a kid that they had on their boarding pass? It was A, B, C, D, E, F, something like that. Yeah, so the kid's name was this. Yeah, right. That was the kid's name, A, B, C, D, E. And apparently the person at the gate made light of it. And the parent got upset and said, it's Apsity. That's how you pronounce it, Apsity. Now, it makes sense after the fact, but you can't name your kid that and expect nobody to say anything. Because the flight attendant or the gate person maybe thought this was a typo, like something weird happened on them. That's a bad random name generator. Well, it already happens because you can legally change your name. Legitimately, you can legally change your name, but you would add that would happen more often if people's names were randomly rolled, and then you had to pay for re-rolls. And you could pay for all sorts of highway fixes and stuff like that. you have the billionaires, you know, their kids that were on like roll 230,000 until they get a name that's, you know, they accept. But this is dehumanizing. We can't do that. It's against the rules. Sarah says it's against the rules, and I'm going to go with that. All right. So in any case, the parent might want to keep track of their kids' names. In this case, our inhuman process IDs that are living on the computer. So perhaps we go in and we create an array of process IDs, which are just integers, right? So we can come up here and we're going to go ahead and again we'll make it global, so we have access to it scope wise and all the other things. So we'll say int. Let's call it kid PIDs, something like that. And I don't know, we'll say we can have up to 1,000 kid PIDs just because for this. We're going to be wasteful, and that's okay. But we always know the number of children we currently have. So we know how far into this our kids are, right? All right, so every single time a parent, and actually, why don't we do this? I'm going to not increment beforehand. Let's increment. Let's have the parent always increment that. So the very first kid thinks they're kid 0, kid 1, because kid 0 will live at bucket 0 in that array. Okay. So we'll remove that from there. We'll put it inside of the parent's handler, or the parent's else part of this. So the parent will increment their number of kids, but before they do that, they're going to go ahead and say kid PIDs at bucket num children is equal to PID. We'll remember this particular kid's process ID, then we'll increment our number of children. Then we'll sleep for a second, and we'll go ahead and tell this kid to go away, something like that. All right, so now what we want to do is we want to understand how our arrays copy, because the statement we keep making is that when the fork system call gets called, the children get a copy of all memory associated with the parent. So we already proved that this child knows which child number they are, but they should also know the process ID, potentially, of all the children up to and including them, right? So for int I is equal to 0, I is less than num children, I plus plus, we're going to do something. My siblings are kid PIDs at bucket I. And actually, let's do this. I am child number that with PID get PID. So our child will say, I'm child number 0, 1, 2, 3, whatever, and then they'll say what their process ID is. And then they're going to go through the array of children, printing out the process ID of all the children up to, including themselves. Okay, so let's see how this works out. So now instead of a typical primitive type, we are giving our parent a copy of kid PIDs. And actually what might be interesting to see here, printf my array's address is %p. kid PIDs. Okay, so we're going to show the address of that array for each child.
I have a question.
Go ahead.
Is it gonna print out like its process ID twice because you're going like through the length of the array and the last entry would be the
Correct.
process ID that you've already printed?
Correct. Yep. Actually, hold on. Probably not. The reason it's probably not, and it's a good question, is the child well, let's see. The child gets a copy of that array immediately. That child's process ID is not added to the array until after the fork system call. So actually the fork system call doesn't know about this child. The child can get their own process ID by get PID. But right here, when the fork system call is created, is called, and the child gets a copy of all memory from the parent, that child's process ID has not been added to that array yet, because the parent or the child got the copy right here. And not until we've branched to either in here or in here, if you're the parent, does that child get added to this and then increase the number of children that were created. So really the collection of children that a child will get is everybody up to, but not including them.
Yeah, that makes sense. Thanks for clarifying that.
How does the parent know what the child's PID is there? Because
That's
isn't
what
PID always going to be 0?
Nope. PID is 0 if you're the child, if you're the clone. But if you're not, if you're the original parent, PID here is the child, is the process ID of the child you just created. So the parent gets the birth certificate, they get the actual process ID for the actual child that just created in the operating system, where the child themselves says, okay, look, I don't really have an identity, I'm new, I'm just kind of out here in the world. So that's why we asked this question immediately after calling fork. The fork system call creates a duplicate process. And what we're really asking here is, am I the copy or am I the original? If I'm the copy, PID holds the value 0. But if I'm the original, PID holds the unique process ID of the child that I just created. That's how the parent knows that.
So each process looks at that variable and gets a different answer.
Correct, exactly.
Okay.
The child looks at it. That's how we're able to ask this question. The child says, hey, what's the value of PID? If it's 0, the child's like, man, I'm the clone. I'm the copy. Oh, it just reminded me of another movie.
I have another question.
Go ahead. Then I'll go off topic with my movie.
So when you call the fork command from the parent and then it duplicates another process,
Yep.
At what point or what line in the code would the child process start at after the fork's been called?
Between 39 and 40. So immediately, the child process is born right here. This guy blocks until the process, till the new process has been created.
Okay, thanks.
I'm trying to think. It was Michael Keaton. There was a movie with Michael Keaton in it. I think it was called Duplicity, where is a hilarious movie where, he's this guy living he's living a normal life and he can't keep up with all the chores. He finds some this new science place that's dealing with cloning and stuff. He goes in and he clones himself, so now he can get chores done twice as fast. And he starts, oh, this is pretty handy. He goes so then the clones start making clones of themselves. You can imagine all the hilarity because he's married, so now you got the wife not knowing about the clones and all sorts of stuff. But one of them is a little special. It's the whole make a copy of a copy situation. The movie is really funny. But I mean, it's probably from the 80s or 90s, probably 90s, I think is the movie. I think it's called Duplicity or something like that. Michael Keaton. Worth watching. Okay, so anyways, so does that make sense how the fork system call works in terms of what the value of this variable is? It's either 0 or the process ID of your new child. So now what we'll do is the parent adds that child to the array of kid PIDs that everybody has a copy of, but the copy they have is the copy that was made at the time that they were born. Okay. The parent is the only one that gets this perpetual growing copy. Parent goes to sleep, and then, sends the signal to the child. The child does the same thing they did before, showing what they know. And now they're also saying, hey, look, this is the address, the pointer of my array. And here are who my siblings are, going through the collection of that array only up to themselves, and well, only up to the child before them, because of where I'm incrementing now. So we'll go ahead and run this. What did I do for a misspelled printf? Clancy. He's not even in the class. Yeah, still his fault. Too many arguments. Oh, because I just copied it in this guy. Oh, I didn't finish my PID thing. This is the point, I think, where we hit the Michael Keaton movie, probably. Multiplicity. Yeah, thank you. All right. So here's the, notice that the number of children keeps increasing. These are the siblings for this particular child. And we'll finally kill them off. Okay, so and let's go review. This is the memory address of that array. 561322E07040. Is that the same memory address? Is that the same memory address?
Yeah, that's what it looks like.
Yep. So remember, the children get a copy of memory. They all got a copy of if we go back here to our code, the children all got a copy of parent HP, right? Which is an int. They all got a copy of num children, which is an int. They all got a copy of kid PIDs. Now, this variable lives somewhere in memory. So I'm gonna show you something here. I'm gonna say printf my array variable is located at %p \n the address of kids PID. Okay, that is the address of this variable, not the contents of the variable. Kids kid PID is a variable of type pointer. It holds a value, and that value is of type memory address. Just like this guy, parent HP holds a value, and the value is of type int. And the children got that value, the current version of that value. The children got the current version of this value. The children get the current value of kid PIDs, which does not change, right? We were incrementing, we changed parent HP, we were incrementing num children, but we didn't actually change the value of kid PIDs, did we? We added things at that memory address, but we didn't change the value of kid PIDs. The value of kid PIDs is a memory address, which is the base address of that array. Now, The children, though, each got their own copy of this variable. So even though the variable holds the same value as we saw here, right? That value is the same as all the other ones here because they got a copy of all the variables, including the values of those variables. This is us making sure that we understand that an array, a pointer, kid PIDs here, it holds an address which points to where you can find that collection. But the value itself that is stored inside of kid PIDs is a memory address, which is really no different than an integer, right? It's just a primitive value. But the variable itself, kid PID, that variable lives somewhere in memory. The address of where that variable lives will have changed because the child gets a copy of all those variables. So even though the value stored inside the variable is the same, the location of that variable in memory for the child will be different because it had to create a duplicate of those things in memory. Let's see, did I finish changing in here? Kid PIDs, here's the address of it. So these two lines here are very important. This first line is gonna say, where does my variable kid PIDs, where does that variable live in memory? Not its contents, but the variable itself. Where does that live in memory? That's where I use this little ampersand thing. I say, tell me the address of this variable. As opposed to this guy saying, tell me the contents of this variable. What value does kid PIDs hold? It holds a memory address, which we're going to print out. This guy will become a memory address, but it's not the memory address that this variable holds. Instead, it's the memory address where this variable lives. Does that make sense? So if we go back and run this again, did I ever kill this off? It's just been trucking. Oh, I think I had killed it off. Stop it there. D16, A64, 2040, my array variables located. 5, those are all the same as well. I wasn't expecting them to be the same, but maybe because it's a pointer type, they decided not to duplicate it. Because I think that the child, I think the integers are going to have different memory addresses for the memory address of that variable. Although, wait. It's showing me my array variable is located. It's not dereferencing it. This is showing me the same thing that is inside of this variable. See the contents, it's the same. So the address of PID right here, or I'm sorry, the address of kids PID is the same thing as just saying kid PIDs and doing it as a pointer. Why is that? Because this is a variable name. Here, I'm going to just do something here real quick, just as a quick test. I'm going to print out the address of num children. I think that should be a different value since that was a primitive to begin with. Two eight. No, it is the same value. Okay. Well, if that's the same value, then if we change a value at that address for an integer, the parent would, well, or any of the children would also see that. We should be able to notice that here. will force the issue. So we already have our parents handler. Does the parent register themselves? They do not, but we'll go ahead and have the parent register themselves. And then we'll do a printf parent num children is now %d num children. And then what we'll do here is after this child runs through all of his siblings, he's going to say num children is equal to, I don't know, 41,275, a much bigger number, right? So we'll have the child arbitrarily change that value, which according to this lives at the same place in memory. This is the memory address of the variable called num children. And all those children are getting that same address. Although I guess I am presuming that the parent has that same address. We can prove that real quick. That address %p address num children. Like that. So we should see those match up. And then what we'll do is we'll have the child, after they've modified this, they'll send kill sig user 2 to get, actually it's, you got to send the process ID first, right? Get PPID sig user 2. And just for the sake of argument here, so we don't, we'll sleep for a second, we'll send the signal to our child, and then the parent will pause, waiting for the child to write back, something like that. Based on what I'm seeing here with the addresses being the same, the parent's gonna see the updated value. Kind of exciting. Did I compile? I did compile it again. Num children is now 1. Yeah, so it didn't actually change. And the parent says, here's the address of my here's the address of my num children variable. And we definitely changed it at that address. Just one more thing to force the issue, just to make sure. I can draw a conclusion based on what I think it is now, but we're gonna say, set the value at this address equal to this number. So this is going to get me a memory address, and I'm going to say put a number at that memory address that is this one. I'm pretty sure what we're seeing here is protected memory to keep processes from running amok on the operating system. Make sure. Yep, parent has a 1 value. So what I'm thinking is occurring here, if I go back and draw a picture, which makes some sense for a modern operating system, I guess, but really does force us to use inter-process communication, well, things like shared memory, if we want to share stuff, share actual values between processes, is, I believe, let's just set this to the back. This yellow that I have here represents kind of like a virtual environment where every process that gets launched in the operating system gets its own little virtual environment, and the addresses that are handed out are relative addresses to this environment itself. So these 4 processes all had a variable with the same address, but that variable had an address that was locally looked up in their own little environment, as opposed to those things being an address in the global environment that they could access. Does that make some sense? Good thing about that is, I think I told you in a previous class that we had an issue historically where you could just keep creating child processes and have it take over the operating system. Well, now you probably can set a limit on the number of virtual environments that are allowed that doesn't supersede the number of total processes allowed on the system. So this is seemingly a virtual machine type solution before we had virtual machine type solutions like we do with Android and the Java ecosystem. So that's why when we come back over here, we're seeing this variable living at the same location as this variable, living at the same location as where's my child, as this variable as a child. And the child is changing the value at this memory location, but the parent doesn't recognize that change because the change happened inside of the child's local environment. And this is all okay because we can ultimately conclude, if we want to share data between processes, we need to use IPC system calls like shared memory. Because I think one thing we would see here is if we, see, I'd have to change it after the fact. Well, here, we could do it with a child. A child here can go ahead and set bucket 0, kid, well, here, we'll have them printed out first. Then we'll say kid PIDs at bucket 0 is equal to 21,222. Something like that. Changing it, this should effectively be doing the same thing. So the next child we see should show at bucket 0 that thing if the data was shared. And we're not seeing that, right? We're seeing actual process IDs. instead of that 21,000 thing. So even with an array, which was passed by pointer, those arrays still are living in their own little environment here. All right. So as of right now, the parent has a collection of all these things. The child gets a copy of that in and of itself at that moment, including real process IDs, but the child can't communicate back to the parent through that array. We're not going to need it to do that to accomplish this task, but they can't do it, even though it was a pointer. All right, so we'll stop there. On Friday, we'll come and finish this up using shared memory, and then we'll go from there. I will see everybody on Friday.